is the math that is hard. One of my pet peeves is like the little doll that you pull a string and it says things, and one of the things it said was, math is hard. You know, that's, it got a lot of abuse for the inappropriateness of telling little girls that math is hard. Gender change. Yes, now if it was little G.I. Joe and G.I. Joe says, math is hard. But no, this math is hard. This is where we ended last class period. Finding, okay, did we really find these? We did no work to find these solutions. We just said those are they. I wish that I was going to do that today as well, because today's is no picnic either. But I guess compared to this, it's easy. So what was the important thing that I pointed out at the very end of class yesterday?
That these give us our conditions for what L has to be.
Yes, that it gives us that the absolute value of M has to be greater than or equal to, it doesn't have the equal here, should have, greater than or equal to L if it's, that's right. It's right. If M is greater, if absolute value of M is greater than L, you don't have a solution, is what that's saying. So that means that absolute value of M must be greater than or less than or equal to L, which is the correct. So that is correct up above. And so, for starters, where this comes out as something useful to you, if L is equal to, okay, you guys know about spin, and every electron has that spin and down spin. So we have to double everything we're going to get here. So if L is equal to 0, what values can M sub L have? Trick question, because I said plural. Go ahead, Chad.
If it's 0, double it's still 0.
It's got to just be 0. So you only have one possibility for L equals 0. And that's what we have in the first row of the periodic table. We have only one possibility. We have 2 spins. That's why there's 2 in the top period. If we go to the second period, then we're going to have the L equals 0 and the L equals 1. Well, if L equals 0, that's going to have one value for M. If L is equal to 1, how many values do you get for M?
2.
Not 2. What values can it take on? If L is 1, M could be, absolute value of M has to be less than or equal to L. So it could be 0, 1, or not minus 1. So you have 3 values that you can have for M if L is equal to 1. And so you have 3 values for M for L equals 1 value of M for L equals 0. So that's a total of 4. Double that, and you have 8 elements on the second period in the periodic table. Right? That is why they're there. It's not coincidence. Now, what does seem wrong is, if L is 2, how many values of M can you have? You can have 5 then. 2, 1, 0, minus 1, minus 2. So that means you're going to add in another 5 times 2 is 10 states. But if you look at the third period, au contraire, how many do we add in the third period? We don't add any, it's still A. That's because, as we'll learn, the energies for the L equals 2 values are actually higher than the energies for L equals 0 and M equals 3. And so that's why it doesn't appear until the fourth period. And so the numbers we have in the rows come directly from this mathematical relationship we found. And so we're going to come back to it, but I just want to make sure you understand this really is a significant result. And even though we did nothing to derive these, we could see how that result had to occur based on the form of these two equations. So the complete angular solution now. This is true for any central force. It doesn't have to be a hydrogen atom, but that's the case we care about. For any central force, your angular distributions are going to have these, what we call spherical harmonic functions. So let me highlight the word spherical harmonics. Oh, actually, it's the title of the slide as well. And those spherical harmonics have this symbol. And that's the normalized spherical harmonics. Notice the normalization constant has both L and M in it. And they have e to the im phi, p, subscript L, superscript M of cosine theta. So you've got to go through that, the associated Legendre polynomial, or associated Legendre function. I get the two confused, to put it all together. And I'll probably give you a problem where you have to do that. It's not fun, but at least gets you into feeling that this is how it works. Here's the outcomes. So, right, I give you, when I say find y something something, here's the table with a whole bunch of them. You know, y0, 0. What does that mean if you don't have any phi or theta in it? Well, what are these spherical harmonics telling us? They were the solutions to what part of our wave function? Okay, we broke our wave function into r is the radial function times y, this, which is an angular function. So if it's constant, that means it's going to be spherically symmetric. So y0, 0 is spherically symmetric. If we look at these others, well, let me just zoom. Can you find anything else that is spherically symmetric here? I don't see any others that are spherically symmetric. So, right, this depends on theta and phi. This depends on theta. So that's the only one here that appears to be perfectly spherically symmetric. It doesn't matter what theta and phi is, it's going to have the same value. Yeah, good enough for that. We will later on go to this website called Orbitron once we get the radial solutions. So now we're going to do the radial solution. And when you look at this at the face of it doesn't look that tough. It really doesn't. You have a function with r, capital R, lowercase r. It doesn't look that bad. In fact, it's a lot like the regular Schrodinger equation, except this term here, well, actually, let me get rid of that. I'm sure there's an undo button there it is. Let's look here. We're going to change it to make it so it looks really much more normal. We're going to change variables. So we're defining u is variable r times function r. Why would you do that, you ask, right? Don't you ask that? I mean, you know that the reason has to be it's somehow going to simplify. But it seems really odd to say, well, my function f is going to be x times, well, let's say g is equal to x times f. Why? Well, when we put that in, then we have it simplified to this here, which looks exactly like our normal Schrodinger equation. Right? We have minus h bar squared over 2m, d second u dr squared, plus something times u equals eu. And the something has the v, but it has an additional term. This term here is called the centrifugal term. Now, what do you know about centrifugal force? It's not real, yes. It's a fictitious force. But it's called the centrifugal term because it's going to cause the radius to move out a little over what it would have been without it. And so the effective potential is the actual potential, what we've already learned, plus this centrifugal term. And here's where I talk about, this is where I talk about the centrifugal term. By the way, notice, if L equals 0, there is no centrifugal term. Right. Now, this here is just an interlude to whet our appetite for how we find solutions. So we're going to take the example of a three-dimensional well. This is actually very appropriate for something like talking about the nucleus of an atom. The nucleus of an atom we treat as a three-dimensional potential well. So you have essentially inside the nucleus, the nucleons. We talk about like how a particle bounces around. It can be anywhere in there with no potential. And then it has a potential limit. It's not infinite, it's finite, so it's particle in a finite well. And it can get out. And that's how we can calculate things like how radioactive decay occurs. So if we use this, then inside the well, V is 0, and so we just have this for a Schrodinger equation, just set the V part equals 0. And so this K here is combining, well, it's taking the energy E and combining with 2m over h bar squared, so that you could make it a simple thing instead of having E 2m over h bar squared there. And since it's k squared, then k is square root of 2m e over h bar squared. Anyway, so we have this, and what did I forget? I forgot something. U. Can't forget that. It's a completely different problem if it's equal to a constant. So in this case here, what would you do for your solution?
Sorry, so you just divided everything out to the other side, or subtracted over and divided?
Okay. So the first thing was I subtracted EU from both sides. And then I divided everything Actually, I should have done it the other way. Looking at what I have there, I moved it the other way. I moved that term over. It's the same. Divide everything by minus h bar squared over 2m. Get rid of that equals 0 because that's not what I did. And so I have d second u dr squared equals L times L plus 1 over R squared U minus 2ME over H bar squared U. And so that's where we then defined that. And so then that gives us, factoring the U.
That is the same K that we had before, right?
It is. So now this here, it looks just like what we had before, except realize we have the 1 over R squared in there. So it's not just going to be an exponential result. So how would you go about trying to find a solution to this with your very limited differential equations experience?
Well, you could try to separate variables, but I'm not sure if that would work in this case.
Well,
It's just
yeah, we really only have, we're down to one variable. What did we do for the analytical solution for the simple harmonic oscillator?
we defined variables to simplify it, and then
Okay, we've already done that.
we've done that.
Sorry, is R and is R not a variable?
R is a variable, yes. U is a function, R is a variable.
Isn't that two variables then?
Well, the so you're thinking put like d second u over u is equal to dr squared times this stuff. The problem is we have d second u and not just a du. But what we did was we said, well, what's the solution for large R? That was the first thing we did. So let's look at this case. If R is large, what does this become? So it's just minus k squared u. So if it's minus k squared u, now we know how to find the solution. That's going to have a solution of the form e to the b. And if you take the second derivative of e to the b, you're going to have b squared u equals minus k squared u, which means that you have equals plus or minus ik, which somehow I've got a sign error here because it should be no plus or minus I, it should be just plus or minus k. Let's go to the next slide and, oh. Say that again?
I was just wondering if we defined k correctly.
What we I am, well, I actually am correct. I am correct because my solution was for large R. The solution that's on the next page is for L equals 0. What's the difference in large R and L equals 0? The only difference is going to be your condition. If L equals 0, this term is 0, right? And we still have it. So instead of R is large, let's just put L as 0. And then, so my work was correct. Then we just have an e to the plus or minus ikx, or ikr in this case. And e to the plus or minus ikr gives you sinusoid, and when you apply your boundary conditions, it turns out that you just have a sine function. Now we're going to stop there because for all other cases, the solutions are Bessel functions, and we don't want to do Bessel functions right now. Oh, and Neumann functions. Don't forget Neumann. I think it's like Baron von Neumann or something like that. So let's go to the hydrogen atom. That's what we're here for. That's, right, the whole periodic table we will understand from our work with the hydrogen atom. We won't do the whole periodic table because you know it can be solved exactly, the hydrogen atom. Using perturbation theory. Now, we're not going to get into perturbation theory in this class. We just don't have enough time. Take a second semester, we'll get into perturbation theory and talk about it. But we can solve the hydrogen atom exactly. Everything else we can approximate, or, well, maybe a little more. We can solve any atom with a single electron. See, if you have 2 electrons, then we start to have problems. If you have more than 2, we have more problems. So we can solve exactly if we have only 1 electron. So I have this just because I'm like, what kind of person gets a hydrogen atom tattooed on their neck? Yeah, not many of us would be willing to do that. But the potential function as we established last class period is minus k e squared over r. Why is there a minus sign? Because one of the charges is plus e, one of the charges is minus e, and it was k q1 q2 over r. So there's our potential energy function. In my work, I'm going to use this rather than k. The reason is I don't want there to be confusion between k's, kappas, and the 1 over 4 pi epsilon 0. So I'm carrying more annoying things to write to avoid some confusion. So here's the first thing that would be confusing. We're going to define kappa here as minus 2m e over h bar squared, all square rooted. And the first thing to say is, why a minus sign? Any idea why there's a minus sign there? If you know the end, it helps you to answer that. What can you tell me about the energy of an electron in the n equals 1 state of a hydrogen atom? I'll give you a clue, 13.6 and EV are in it. But what's the other part that it is? It's negative. And because it's negative, that's how we have kappa defined with a minus in there, so it's going to give us a real value for kappa.
Okay, so the angular solution, that gave us M and L, and this
Yes.
one is going to give us the N's.
That's what it's going to give you, yes. That's good logical deduction. I know we have N, M, and L, and we've only done M and L, so this must give us N. So this is the one, right? We didn't have any energy outcomes that we've talked about from the angular solution, but we are going to get energy from this. So we have this kappa defined, and as you may expect, we're going to change variables. Now we already have U here, but we're going to go a step further and change from U. Isn't that nice? Because, I mean, how easy would life be? Actually, okay, we're not changing U, we're changing R. We're defining rho is equal to kappa R. So rho is our new variable instead of radius. But you can always calculate the radius from rho by using this value for kappa. Why do we do that? Because you can see this here became a much shorter equation. It's the same equation as this, but it's much shorter and easier to read. Okay, how would you solve this? Using the harmonic oscillator as a guide, how would you solve this? And it's not going to be with the ladder operators.
The Taylor series?
That's the last of 3 steps. Or no, yes, last 3 steps.
Just solve for a really big rho first.
Yeah, we'll solve for really big rho first. So if rho is really big, what does this thing in the bracket become? 1. Okay, so that's easy. For very big rho, much greater than 0, that's going to be very big for me. Then I have d second u d rho squared equals u, which has solution of e equals b, or e to the b rho, and then we get b squared equals, b squared equals 1, right? And so b is equal to plus or minus 1. And so that would give us u is equal to e to the rho plus b e to the minus rho. Now we're almost done with this first version of our solution. What's the last thing I have to do with this?
Use the boundary.
Okay, I have to make sure it's normalizable, which is the only boundary condition we have here. And so to be normalizable, what is rho going from? What's its minimum value? Just think of rho as radius since it's linear proportional.
So 0.
0. So if rho is 0, that would be a plus b, right? Well, that's normalizable. And then what's the other limit for rho? That would be for an angular thing. This is radius.
So the distance between them.
How far can the electron get from the nucleus?
Infinitely far?
In theory, infinitely far. Now, we never think about that, right? We always presume that the electron, if the electron's bound to this proton, it's going to be in this small region, much smaller than if I put my fingers together. But mathematically, it could be all the way to the moon or outside of the solar system. It's just not realistic. And so that means rho can go to infinity. Well, if rho goes to infinity, one of these things got to go. Which one has a problem?
A.
Yeah. Either the rho goes to infinity if rho goes to infinity, so A has to be 0. And so we get here, A equals 0 to be normalizable, to be. And so we just have, and I'm just going to put e to the minus rho because I'm not worried about what the normalization constant is until I'm all done. So that's our u for large radius. Now we're going to come back and say, okay, now that I have my u for large radius, okay, so we've already done, I had them in opposite order. That's why b was equal to 0 here. It's still the same outcome. So now let's turn the solution for small radius. So for small radius, I have, and let's just come back and look at this equation. For small radius, 1 over rho squared is going to be much bigger than 1 over rho or 1. So for small radius, only the 1 over rho squared term is going to persist. And so we have, this is the Schrodinger equation for small radius. And if you solve that small radius equation, this is a differential equation that you've not done. You get u is equal to c rho to the L plus 1 plus d rho to the minus rho to the L plus, minus L. And since this is for very small radii, as rho approaches 0, as rho approaches 0, rho to the minus L is approaching infinity. And so that term's got to go. It's also not going to work out for us. So we only have this term for the small solution. And so then our total solution, and this is what you said, our total solution will be the small solution times the large solution times an infinite series to fill in the gaps. And remember that infinite series could be any function. I mean, if you want it to be, problematic, you can say, why didn't you just start with the infinite series? Wouldn't that be also a representative of our full solution? The answer would be yes. Yes, it would be. But it'd be a lot harder work to go from there. So it's easier to start here doing the large and the small radius solutions and then do the intermediate one. Here's where math is. So we have our u, we have our v, we have our Schrodinger equation. We put it all together. I don't want to. I really, really don't. I worked on it this morning for, 45 minutes. I was making good progress, but it's slow going. So here's what you get. If you take the first derivative of u, take the first derivative of u, that means I'm going to have the product rule 3 times. So I have 3 terms. One bringing down the L plus 1 and having rho to the L. One bringing down the minus and then having the same thing, and then one with the derivative of v. So when you combine terms, you get this result, which looks a lot neater than most of what I was doing. And then you take the derivative of that because we had to have the second derivative. So now we have to use the product rule a few more times. You have function 1, function 2, and then times these 2 functions and these 2 functions. So there's a whole lot of terms there, right? Yes, I see Aaron's face is showing the pain I was feeling this morning as I was going through this, just to make sure I didn't make any mistakes. So if you look in your textbook, if I remember right, it was like page 156, which I know you don't have your textbooks out, but I got mine so that we could make sure. Nope, not 156. It's starting on page 145, so this is actually on page 147. And of course, he does the same thing. He just goes straight to these equations without showing you all of the work. And I think we can all recognize that's going to be painful work. So if this is the second derivative, this is what I have to work with. with all of those stinking terms. I think I'm funny, by the way, when I make these slides and I put titles and calculus ensues. Every now and then I put something up there that it said math that is hard, not math is. Okay, so if we take this, and for reasons God only knows, my plan is to actually do this in front of you here. You know the odds are 70 to 80% I'm going to make a mathematical error with the enormity of this, right? So we combine these. Do I really want to do this? What was that?
That's how I feel with the homework.
Yeah, I know. Which when combined. Yeah. Well, we're going to have 1 minus rho naught over rho plus L times L plus 1 over rho squared all times rho to the L plus 1 e to the minus rho V is equal to all of that stuff. Okay, I can only go so far. Right, I substituted this this here and this here. That's what I did. So I put those together to give me the right side of this equation. And the left side I left there because that's a lot. Now, you'll notice we have here terms that this is rho to the L plus 1 times 1. So I'm going to have a rho to the L plus 1 term. And then if you divide that by rho, I'm going to have a rho to the L term. If you divide by rho squared, I'm going to have a rho to the L minus 1 term. And when we look over here, I have rho to the L times this stuff. So that's a rho to the, actually, yeah. And then times rho, so that's a rho to the L plus 1. And then divide by rho, so that's a rho to the L minus 1. So those are terms that can be combined. And so when you combine them, you get something that looks a lot better. That's actually, I think, prettier than either side of the Schrodinger equation on the previous page was. Now, does that mean it's easy? No. But it's doable. So now we have V was just this infinite series, and we have a second derivative, a first derivative, and no derivative. So we have to calculate the first derivative and the second derivative. Remember when we did this with the ladder, or not with the ladder operator, with the harmonic oscillator? Doing that first derivative, I just brought down a j and lowered the power by 1. How did I go across that equal sign? What's going on there?
Set the series one integer higher.
Yes. What you do is you put an intermediate. You say, okay, let's call this sum over m equals 0 to infinity c sub n. Okay, m was a poor choice because m is one of our quantum numbers. A. Is A free to use? C sub A times A rho to the A minus 1. And then we say, well, let's let J plus 1 equal A. And so we just go ahead and rewrite the same thing. This would be starting at j equals 1, right? Or j equals minus 1. Now we're not to what it had because of one thing. This is starting at j equals minus 1. How did I get starting at j equals minus 1? I had starting at j plus 1 equals 0. So if I subtract 1 from each side, that becomes j equals minus 1. Now, if I start with j equals minus 1, j plus 1 is equal to 0. And so I'm going to get 0 for the first term here, which means I can rewrite this. It's equal to c to the 0 times 1 minus 1 plus 1 times rho to the minus 1 plus sum j equals 0 to infinity So here I've put it explicitly. Here's the first term, and here's the rest. But this first term, minus 1 plus 1, is 0. And so this summation here is equal to this. And that's the actual substitution. I know I spent way more time than I should have on that. But I just want to make sure it's real clear that it's legit math, that it's not some kind of fancy voodoo. Because most of what we're doing today is some kind of fancy voodoo. No, it's all legit. And then this here is taking the derivative of this form. Take the derivative of that, and it gives you this. So you bring down the j, and it goes to j minus 1. And yeah, that's all it did. So now we substitute those in. So we'll put this in here, and for this term, we'll use this one. For these two terms, we'll use this one. And then over here, oh wait, that was wrong. Oops. This one, second derivative is there. This is first derivative. This one here was going there. And then for the function, of course, that. Why did I have this convoluted set of how I did it?
So you wanted a certain order of row.
Yes, I want them all to have the same order of row. So this first term, rho times the second derivative of v is, wow, okay, used up all my space. Excellent. Well, I'm going to have rho to the j minus 1 times rho gives me rho to the j. Then the ones that I have here with blue, rho to the j, there's no rows there, so it stays rho to the j. Then this pink one here, rho to the j minus 1 times rho will give me rho to the j. And then for this last one, because there's no rows out here, I have the form that I started with of rho to the j. So everything is going to be the same order of row. I didn't write it because I was like, I'm going to do this in class. Okay. My phone is ringing. My hand is buzzing. This is great. So writing it out, I have rho sum over j equals 0 to infinity. First term, and then this one is going to be then the next one minus rho using the other DVD row. And my final term And all of that's equal to 0. So there I've put it all out, and you can see that bringing this row in here gets rid of that. So it's rho to the j. This one here is rho to the j. Bring this in, it gets rid of the minus again, it's rho to the j. And this one's rho to the j. So they all have the same power of rho, excuse me. So now, how is this useful? This equation has to be true no matter what rho is, right? I mean, it's a given. And because I have rho to the j, for each power of j, it's going to have to be independently true. So I just take for a given j, so just go through here and say, okay, let's take a given j. I'm going to have this stuff here plus this stuff, here, minus, because there's a minus sign there, this here, plus this stuff here in the Cj has to equal 0. So it gives me an equation which I simply don't have the space to write. C sub j plus 1 times j plus 1 plus C sub j times 2L plus 1 minus C sub j plus C sub j rho 0 minus 2L plus 1 gives us that equation. Now, what's beautiful about this is it has C sub j plus 1 and C sub j. So what I can do here is I can say C sub, I'm going to change colors. C sub j plus 1 is equal to C sub j times, and if I move all the C sub j's, all the signs, I'll have, and then the others will be minus.
Why is the C term in front of the 2 times L plus 1? Why is it a Cj instead of a Cj plus 1?
Which one?
So for the second term,
Ooh, that's a mistake. That's a mistake. Crud. So it's, I'm going to have 2 terms, right? That's 2L plus 1 times C sub j plus 1. Yeah. Okay, so I should have had a second term here. Okay, so I'm going to erase this because, yeah, I made that mistake. So if I had not made mistakes, I told you the chance of me going mistake-free were about 20%. This is what I should have had when I do it. So both of those terms were combined, and then it was rearranged to give us j plus 1, j plus 2, L plus 2. So this gives us a relationship between the C sub j's. And finally, and this is where we'll stop today, there must be, in order for us not to overpower our exponential term, our polynomial has to terminate. Doesn't matter at what j it terminates, but it has to terminate. So there has to be a C sub j plus 1 that's equal to 0. And so that defines a j max. And that j max, then, we define n is equal to j max plus L plus 1. N is our final quantum number. So what does n tell us fundamentally? It tells us the highest order term in our polynomial. But notice it's highest order term plus L plus 1. So it's not equal to the highest order term, but it tells us what it is. So that's our final quantum number. We'll pick up there next week.